Okay, so for today topics, we're going to look at the carbohydrates, okay, which consists of the atoms of light, carbon, hydrogens, and oxygen. Okay, so be careful when you write it, say consisting of carbon, hydrogen, and oxygen, full stop. You wouldn't get the correct definition of the carbohydrates, because when you talk about hydrogens and oxygens, if you put these two words, they basically means the gas. Okay, so be careful when you write. It should be carbons, hydrogens, or it must be carbon, hydrogen atom, okay, and oxygen atom. And generally, if you look at the ratio between the hydrogen and oxygen, it will be always in 2 to 1. Okay, so that's why the word carbohydrates, carbo mean carbon, hydrates mean water, so H2O. So the hydrogen and oxygen in the ratio of 2 to 1. So therefore, the empirical formula of carbohydrates always in this form, okay, where M can be equal to N or M not necessarily equal to N, okay, it doesn't matter, okay. So there are three main groups in carbohydrates generally, where we're going to study. So we have the monosaccharide, means only one. Okay, disaccharide means two, di means two, poly means many. So means that in this case, monosaccharides, they are monomer. So we use a monomer to form disaccharides, means it's two sugar molecule joined together. And then from this, we can continue to add on many glucose molecule to form a polysaccharide. In the lesson before, we learned about the oligosaccharides, means short fragment of sugar. So what means short fragment of sugar? So perhaps you have about like 10 to 20 sugars that join together. That is termed as oligosaccharides, which is not in our syllabus. But if this term come out in the exam, you should know that oligosaccharide means that shorter than the polysaccharides, but longer than disaccharides. Are you clear? Okay, so for today, our focus will be in monosaccharides and also disaccharides. Okay, so let us look at the monosaccharides. When I talk about monosaccharides, they do have this formula of CH2ON. Okay, N means that the number of carbons, okay, number of carbon N. So generally, the formula can also be written as CnH2nOn. Okay, CnH2nOn, where N equal to the number of carbon. Are you clear? Number of carbons. So in these monosaccharides, they are simplest sugar units. When you use the word simplest sugar unit, means that we cannot break them down into a smaller molecule, but highlight the words by hydrolysis. We still can break down the simple glucose molecule into an even more simplest one, but it's not by hydrolysis, it's by oxidation processes, by other kinds of the reaction, not hydrolysis. So what's mean hydrolysis? From the word hydro means water, lysis means break. So it means that it cannot be broken down by using water molecule. Are you clear? Okay, and all monosaccharides, they are soluble in water to form sweet solutions. So this is another property of monosaccharides. So two properties. First, they are the simplest sugar units. They cannot be broken down by hydrolysis. Second, they are soluble in water to form sweet solutions. So why they are soluble? They're soluble because they contain multiple hydroxyl groups, a lot of OH group. And we do know that O is delta negative and H is delta positive. So therefore, it can actually interact with water molecules. Still remember, the OH group is very important. O delta negative, slightly charged negative. Hydrogen atom slightly charged positive. So therefore, hydrogen atom can actually, with the charge, slight charge of positive, can interact with the water molecule, forming hydrogen bonds. Okay, write down. So because of hydroxyl groups, so they will be able to interact with water molecule by forming hydrogen bonds with water molecule. So therefore, they dissolve in water. Okay, and we do know that all monosaccharides, they are reducing sugar. Correct or not? Okay, when we talk about glucose, we talk about the glucose, we talk about the fructose, we talk about galactose, all of them, they are reducing sugar. So reducing sugar is because of what? Because of this carbonyl group. This C double bond O is termed as carbonyl group. Okay, because of this carbonyl groups, they have the reducing property. So therefore, all monosaccharides, they are able to reduce the Benedict reagent, CO2 plus, which is the aqueous form, blue color, to a precipitate or solid form, okay, which is a red brown color, Cu plus, reducing property. Okay, depend on what? Depends on this carbonyl group. Okay, and this is not in our syllabus, but a little bit we need these informations when we want to explain why sucrose is not reducing sugar. Then we have to look at the locations of the carbonyl groups. So this location of carbonyl group allow us to differentiate the sugar into either aldehyde sugar or termed as aldose, or ketone sugar termed as ketose. So this is how we can group them, or we also can categorize the monosaccharide based on number of carbon atom. So usually 3 carbon atom, we name them as triose. OSE means sugar, tri means 3. So 3 carbon sugar, 5 carbon pentose, where pentagon, right? 5 carbons, 6 carbon hexagon, hexa, okay? So hexose, okay? So in these diagrams, it's not in our syllabus, but I just want you guys to look at it, how to differentiate between aldose and ketose, and whether they are triose, pentose, or hexose. So I will teach you guys to look at how, okay, aldose different from ketose. We look at this. If they are aldose, I will start with the triose as example. You can see that for aldose, sorry, this is aldose. Now, how we know it's aldose? It's aldehyde sugar. Okay, first, basically the name lah. Okay, glyceroldehyde, right? Okay, but how we look at it? You can see, look at this carbon. Okay, this carbonyl group C double bond O always at carbon number 1 if they are aldehyde or aldose. If they are aldose, can you see that this carbonyl group C double bond O always at carbon number 1? So if you name it, then this is carbon number 2, this is carbon number 3. So this is a 3 carbon sugar, therefore we term them as triose. Are you clear? Okay, so that's why we call them as triose. Now, this one, this is ketose. Why ketose? Can you see that the carbonyl group no longer at carbon number 1? As long as they are not at carbon number 1, then they are ketones sugar. So it's termed as ketose. So we can, this is carbon number 1, this is carbon number 2, this is carbon number 3. Can you see that? So again, 3 carbon sugar. So we name them as a triose. But the carbonyl groups are not. Can you see that the carbonyl groups is not at carbon number 1? It's not at the end there. Okay, therefore, it's termed as the ketone sugar called ketose. Okay. So look at this ribulose. Ribulose, okay, you can see that 1 carbon, 2, 3, 4, and 5 carbon. So they are termed as pentose. And if you look at these carbonyl groups, they are at carbon number 2. Okay, this carbon number 1, carbon number 2, carbon 3, carbon 4, carbon 5. So 5, so pentose sugar. So this ribulose is termed as ketose. Okay, we group them as ketose because they are not at carbon number 1. Okay. So this one, carbon number 1, right? So ribose actually is an aldose sugar. Glucose, 6 carbon, right? 1, 2, 3, 4, 5, 6 carbon. And this is carbonyl group at carbon number 1, carbonyl group. So therefore, this is aldose. Okay, how about galactose? Galactose and glucose, they are isomer. Can you see that? So they only differentiate at carbon number 4 here. One is OH at the left-hand side, one is H. But the rest will be the same. And you can see that this C double bond O here, the carbonyl groups at carbon number 1 as well. So again, aldose. Okay. So the last one, let us look at this fructose. They are hexose also because 1, 2, 3, 4, 5, 6 carbon. So that's why hexose. So aldose or ketose depends on this carbonyl group. So this carbonyl group actually located at carbon number 2. Carbon number 2. So therefore, this is ketose. Okay, so what are the role of these monosaccharides? Okay, what are the roles of the monosaccharides? So basically, if you look at this table, triose phosphate, okay, is a triose with additional phosphate group, because triose, they don't have a definite function. They must attach with something. So this triose alone, they don't have any functions, but when they attach to triose, so both of them, glyceraldehyde 3-phosphate or dihydroxyacetone phosphate, both of them actually, okay, is termed as a triose phosphate. They act as an intermediate compound during the glycolysis, so during respiration, and Calvin cycle during photosynthesis. So they are intermediate compound. We are going to learn this, glycolysis and Calvin cycle, in your A2 topic, but I will teach them during your AS. Are you clear? So they are related to a lot of topics. So that's why I teach them during your AS rather than A2. Okay, so then pentose, 5-carbon sugar. So you can see that ribulose bisphosphate, again, they are the carbon dioxide acceptor during the Calvin cycle during the photosynthesis. Ribose and deoxyribose, they are parts of the nucleotides. Ribose and deoxyribose, ribose is for RNA. Deoxyribose for DNA. So these two, at this moment, don't need to worry so much, because we are going to learn them in detail when we are going to study the nucleotides, okay, in your second semester. Okay, ATP molecule also, we need the ribose. ATP, we're going to learn them in detail in chapter A2 chapter, energy and respiration, but I will teach them in your first semester, chapter number 5. Okay, now we are chapter number 3. So 2 more chapters, we're going to look at this ATP. Okay. Now, what you need to know here is the hexose. Okay, hexose, particularly glucose, galactose, and fructose. Glucose highlights, they are the source of energy in respirations. Okay, very important. Their role is as a source of energy. Okay, and also glucose molecule are the building blocks of macromolecule, okay, such as the starch, glycogen, and cellulose as well. So they are not only either we store them or we use them. So we use them in the respiration, or we store them or build as a building block of the macromolecules such as starch, glycogens, and cellulose. Okay, so galactose and fructose. So galactose combine with the glucose to form the lactose. Fructose also combine with the glucose to form sucrose. Okay, so these are the role of the monosaccharides. Okay, so out of so many monosaccharides, which compounds, okay, which monosaccharide we are going to focus more for our topics in AS? We were going to focus on this. The only one monosaccharides that we are going to learn in today's topics will be glucose. Okay, so let us look at the glucose. When talking about glucose, basically we know that it is the most common hexose, 6-carbon sugar. The most common one is glucose. And just now I show you guys the ring, the linear shape, right? You can see that this glucose molecule. So this form, we call them as a linear form. Are you clear? So in solid case, in solids, they form linear form. Are you clear? In solids, they are formed linear form. But when we dissolve them in the aqueous solutions, then they tend to form a ring. So how they form the ring? They form the ring by joining carbon atom number 1 to the oxygen atoms on carbon number 5 and carbon number 6, because we know that they are hexose, so they are 6 carbon. So carbon number 6 is not part of the ring, so it projected out. So if you look at this, this is carbon number 1, carbon number 2, carbon number 3. Okay, if I write it, so this is carbon 1, so carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Can you see that's outside of the ring? Same goes to the right hand side one. So number 1, number 2, number 3, number 4, number 5, carbon number 6. Can you see that? They are outside of the ring. So if you compare these two molecules, both of them, they are glucose. Left hand side glucose, right hand side glucose. What makes them different in this case will be the positions of the OH group of carbon number 1. Very important, carbon number 1. If no, you can see that a lot of OH groups. So which one you are referring to? Okay, so now I want you guys to imagine this is something like a piece of a paper. You try to imagine, imagine you cut out a hexagon shape of the paper, and then you put a stick at each corner there. So you can see that this H, carbon number 1 H, carbon number 2 H, carbon number 3 OH, carbon number 4 H, carbon number 5 CH2OH, they are above this piece of hexagon, right? This is called the ring. So they are, okay, let me highlight with different color. Those are highlights with pink color. You realize that they are above the ring. Can you see that? They are above the ring. Those are color with the blue color, they are below the ring. Can you see that? So, but our focus, because the rest of the parts, they are the same, right? The rest of the part, you can see that they are the same compared to these two. Okay, let me rub it off. Those are annotation. You realize that, guys, the rest of the parts are the same. Only at carbon number 1, where the OH group of the carbon number 1 either located at the below the ring or above the ring. If below the ring, we term them as alpha glucose. It's just a name. Don't ask me why alpha, not delta. Okay, why not theta? Okay, so it's just a name to differentiate between these two forms of glucose. Okay, so the one that below the ring, the OH group of carbon number 1 below the ring, okay, we will be termed, again, will be termed as alpha glucose. And if the OH group above the ring, we will term them as beta glucose. Okay, don't think about, okay, alpha and beta only, but the property will be totally different when we study the polysaccharides. Okay, so now our question here is how we can actually change this linear glucose into a ring glucose. Okay, I'm going to draw it out so you can actually follow my drawing into this activity 3.4. I'm going to show you alpha as well as beta. Okay, now carbon number 1, this is very important. Okay, carbon number 1 join with carbon number 5 later. I'm going to show you. Okay, so now let me draw out this glucose in linear form. So C, so 6 carbon, 1, 2, 3, 4, 5, 6. Number 1 is C double bond OH. It's a carbonyl group. Okay, number 2, we can see the OH, H. Number 3, opposite, OH, H. Then the rest will be H, OH. Okay, H, OH. Now, carbon number 6, you know that's, okay, we have OH, H, and H, correct or not? Okay, but I'm going to simplify it as CH2OH. Okay, so how they form the ring structure? How they form the ring structures? So I'm going to arrange them in the ring form. Okay, so how they do it, sir? So this is C, carbon number 1. Carbon number 1 will have a H and OH. It's OH, O, double bond O. Okay, and then this is carbon number 2, carbon number 3, carbon number 4, carbon number 5. Okay, can you see that? This is carbon number 5. Okay, can follow? So make a ring. Now it's turn to join. Okay, so now carbon number 1 I label here. Sorry, carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Then you will ask, hey, carbon number 6. Carbon number 6 will be outside of the ring. So this is carbon number 6, CH2OH. Are you clear? So this is carbon number 6. Okay, how about carbon number 2? Carbon number 2, we have the H and OH. Carbon number 3, OH, H. Carbon number 4, okay, you can see that, H, OH, okay. And carbon number 5 is C, okay, look at this, carbon number 5. Carbon number 5, this is carbon number 5, right? So you have one H, one OH, and a 1, 2, 3, 5. Sorry, my mistake. Sorry. This carbon number 4. This is carbon number 5, my mistake. Okay, so can you see that? Okay, they have H, so I have drawn OH, have drawn, and CH2OH. Now, what actually happened here is, can you see that? Now, follow. So this H, I use a different color. I use the green color H. So what will happen here is the H actually can come down, join to the O here. Get the idea? The H. Okay. So animations, so remove the H and attach here. Okay, now it's not stable anymore because why? Oxygens have to form 2 bonds. So one with the carbon number 5. Can you see that? So another one have to join here. Join to carbon number 1. So that's why we always say that to form the ring, you're going to join the carbon number 1 with the oxygen atom of carbon number 5. But the thing here, you can see the carbon number 1 have 5 bonds. Cannot be because carbon only have 4 bonds. So we remove 1 here. So do you realize that now my OH group below the ring? So this is how we form the alpha glucose. So in the simple structure, when you draw it for alpha glucose, you can actually skip the carbon. Okay, so how you draw? You draw a ring structure, hexagon with the O at the back. Simplified versions, and you put a pillar. Now, because this alpha glucose, so it means that OH group must be below the ring and H. H, OH. Carbon number 3 is weird one. They're going to have the OH, H, okay, and then OH, H. Carbon number 5, carbon number 6 will be outside the ring, CH2OH, and with the H bottom. So this is a molecule of alpha glucose. Clear? Okay, so it means that the initial H, somewhere here, right? Initial H, now you move it down. Okay, so initially the double bond O, the bonds will be broken. So this is a new bond that formed. The broken ones here cannot. This bond will be broken. Okay, so therefore it forms a complete ring shape alpha glucose with the OH group. Now you can see that. Highlight the OH group below the ring. Are you clear? Okay, so that's why it's termed as alpha glucose. Now, how to form beta glucose? Similar. Okay, how to form beta glucose? So same thing. Okay, so this is carbon number 1, carbon number 2, carbon number 3, carbon number 4, carbon number 5. Carbon number 5 have carbon number 6 here outside the ring, CH2OH, and with one OH group here, and then H, HOH, OH, and then HOH. So in this case, you can see the double bond O above and the H below. Okay, so what will happen here is this H again, okay, I draw it with different color. So this H can actually come to join with O here, okay, in the aqueous mediums. So when it join, so remove the H and let H join here. So as I said that, you can see that the bonds have to be formed between the O of the carbon number 5 with the carbon number 1. Okay, right? This is carbon number 1, this is carbon number 2, carbon number 3, 4, 5, and 6. So again, guys, we cannot have 5 bonds for carbon. We remove 1. So now you realize that my OH group above the ring cannot. Now it formed above the ring. So therefore, this is termed as beta glucose. So the simplified form, how you draw the beta glucose, similar to alpha glucose. Again, you draw a ring structure first with the O. Okay, so with something like pillar. So carbon number 6 always outside the ring. H, so HOH, OH, HOH. Then be careful in this case, OH above the ring for the beta glucose, right? So highlight again with different color. Sorry. So OH group above the ring, because of OH group above the ring, we term it as beta glucose. Okay, so far clear or not? Okay, so we have actually seen how the alpha and beta glucose can be formed, okay, by using the linear glucose, okay, molecule. So linear glucose molecule don't have alpha and beta, okay? Alpha and beta only apply when they form the ring. Are you clear? Okay. One thing that you need to know here is, in order to have the reducing property, we must have this. We must retain this, what we call the carbonyl groups. Without the carbonyl groups, then it won't form this. They won't have the reducing property. So ring form, they won't have reducing property. Yeah. So it means that in aqueous medium, they will be in what we call the equilibrium between the linear and also the ring form glucose. Are you clear? Whether alpha or beta doesn't matter. They will be in equilibrium. So which one will react? This one will react with the Benedict reagent and give us the precipitates, okay, the red-brown precipitate. So means that in the actual aqueous medium, you will have, initially, you're going to have 50% of the ring and 50%, let's say, okay, 50% of the ring structure, 50% of the linear structure. But linear structure will react, correct or not? When the linear structure react with the Benedict reagent, so it means that we don't have 50 anymore. Let's say we have 20 of them, or let's say 30 of them. So 50, then we will move it this way. Can I see that? Try to imagine, sir. Initially, we have 50 linear, 50 ring form in Benedict reagent. Okay, so what they do, they are going to react with Cu2 plus, so that to reduce the Cu2 plus to Cu plus, which is a solid precipitate. Cu2 plus is the aqueous blue color. So first, you can see that this 50 linear going to react. Ring cannot. Are you clear? But this ring and linear, they are in equilibrium. Are you clear? So try to imagine if this 50, 20 of them react. So remaining 30. Okay. Then 50 ring. So what will happen here is the equilibrium will switch this way. So it means that now we're going to have 40 and increase that here to 40, so that it will continue to react with the Cu2 plus. Always remember, only linear structure can have the reducing property, because the ring structure, you won't get C double bond O anymore. Okay, so this is the principle of the Benedict test. Okay, okay.